Section 5.3, fundamental theorem of calculus. In calculus, there are many theorems, but the most important one is this theorem. This theorem is the most important theorem in calculus, from calculus 1 to calculus 3. This theorem has two parts. Suppose function f is continuous. This is the condition to use this theorem. If a function is not continuous, fundamental theorem doesn't hold. We don't have fundamental theorem. So this is the condition to use this theorem. This theorem has two parts, part A and part B. Now, part A. The integral from A to B on the function f, the integral from A to B on the function f is the net area of the region between the graph of function f and x-axis and between A and B. That is the shaded region here. This integral is net area of the shaded region. Now, part A says that to compute this integral, we just need to evaluate capital F at the point B minus capital F at the point A. For this difference, we have a shorthand notation. Yeah, this is a shorthand notation for this difference. What is capital F? Capital F is any antiderivative of function f. So part A says that to compute a definite integral, we don't need to go back to the definition of integral. Definition of integral is tedious. It has 4 steps. Take a review. Step 1, cut the interval AB into subintervals, then build up rectangles. Then make a sum of the areas of all the rectangles. Then take limit. Tedious. So part A, the formula is very convenient. To compute this integral, we just need to find one antiderivative of function f. Then evaluate the antiderivative at the upper limit b minus antiderivative at the lower limit a. That's it. This is a part A. Now, part B. Okay. Take integral from A to x. X is a variable on the function f. This integral now is the net area of the region between A and x. Yeah. This integral now depends on its value, depends on x. When something depends on x, we call that thing a function of x. So this integral is a function of x. Let me denote this function by a. A means area. By a of x. The book calls this function the area function of f. Okay, a of x is a function of x. Oh, it turns out that part B says that this function is an antiderivative of function f. That is, derivative of a is f, function f. The other notation, derivative, if we use d over dx notation, then this equation is this equation. If we replace a by the integral, then this equation is this equation. This is a fundamental theorem of calculus. It has two parts. Now, here is a remark about this theorem. Fundamental theorem of calculus essentially says that integration and differentiation are inverse operations. That is, take integral and take derivative, they are inverse operations. Just like summation and subtraction, they are inverse operations. Multiplication and division, they are inverse operations. E to x and natural log, they are inverse operations. So here, fundamental theorem says that take integral and take derivative, they are inverse operations. Why? Let me explain in more detail. We have a function f. Now, take derivative on the function f. Now, suppose I want to undo the derivative and recover the function f. Then what we can do? We can take integral on the derivative. Yeah, here. Derivative. Now I take integral from a to x on the derivative. By part A, I can compute this derivative by looking for one anti-derivative of this guy. Then what function whose derivative is this guy? The function f. Function f is an anti-derivative of this guy. Because take derivative on function f, we get this. So by part A, this integral is anti-derivative, plug in a, plug in x. Then we get this. You see, f of x is here. F of a is a constant. A is a number. Function value at a, it is a constant. So the original function f minus a constant. So we recover the function f by taking integral on its derivative. Reversely, if we take integral on a function, say integral from a to x on function f, Now, I want to undo the integral. Then what I can do? To undo the integral, take derivative. So okay, here, this equation. Function f. Now I take integral from a to x. A to x. So this guy depends on x. It is a function of x. Now I want to undo this integral. Take derivative. Then we get back to the function f. This equation is part B here. Okay, now here is one example to verify this equation. Okay, the function f is sine. Now I take integral on sine. Say from 0 to x, take integral on sine. To undo this integral, take derivative and integral cancel. Then go back to the function sine. Okay. Now, how to verify this equation? Okay, now let me compare the integral first. Take integral on sine from 0 to x. Okay, x is a variable. Okay. By part A of fundamental theorem, to compute an integral, we need to find one anti-derivative of the function f. Now f is sine. One anti-derivative of sine is negative cosine. Okay. Now by part A, plug in 0, plug in x in cosine. then we get this equation. Cosine of 0 is 1. Distribute the negative sign, then we get this. This is the integral from 0 to x on sine. Now, I want to recover the function sine. How to do that? Take derivative on this guy. Take derivative on the integral derivative. Then clearly negative cosine of x plus 1 derivative is sine. Here are some examples about the fundamental theorem of calculus. Example 1. Find this integral. This integral is the net area of the shaded region here. Now, to compute this integral by part A of fundamental theorem, we need to find one antiderivative of the function ex. What function whose derivative is ex? The function itself. Ex derivative is ex. So ex is an antiderivative of this guy, of this function. By formula, this integral is antiderivative at upper limit 3 minus antiderivative at the lower limit 3. That is this difference. It is the value of this integral. Example 2. Evaluate this integral. Now the function is complicated. Then how to find antiderivative for this function? It is not easy. Before I compute this integral, let me transform the function into powers. For a power, it is easy to find its antiderivative. Okay, now transform the function into powers. Okay, let me split this big fraction into a sum of two smaller fractions. And then write the fifth root as a power here. The first term, x to the third over x to the fourth, is x to 3 minus 4. Basic algebra. The second term, x to 1/5 over x to the fourth, is x to 1/5 minus 4. Now simplify, then we get the function. The function is a sum of these two powers, Therefore, this integral is equal to integral on this sum. Now, by summation formula, I split this sum. I write this sum as the sum of these two integrals. Okay, now constant number 3. I can move it outside the integral to get this equation. For these two integrals, now it's easy to find antiderivatives for them, okay? X to -1 is 1 over x. Then what function whose derivative is 1 over x? It is lateral log. So lateral log is antiderivative of 1 over x. Now, by fundamental theorem of calculus, part 1, this integral is antiderivative, plug in lower limit, plug in upper limit. 1, 2. Then what is the antiderivative of this function? This function, the power is complicated. To find an antiderivative of this function, let's try this function, power plus 1. Okay, try this function. Then by the power formula, x to a derivative is a times x to a minus 1. A minus 1 is a negative 19 over 4. 19 over 4. Okay, now this is a number. This number is negative 15 over 4, this number. Now move this number to the left side. To the left side, then we get negative 4 over 15. Okay, okay, yeah, then we get this equation. This function derivative is this function. So this function is an antiderivative of this function. Okay, now we have antiderivative for this guy. Then by formula, this integral is antiderivative. Then plug in 1, plug in 2. Okay, yeah. Okay, before I plug in 1, plug in 2, let me simplify the coefficient here. This is negative 4 over 5. Now plug in 2, plug in 1. Okay, plug in 2 in x, lateral log of 2 minus lateral log of 1. Okay. Plug in 2 in this function, then we get 2 to negative 15 over 4 minus 1, plug in 1, 1 to negative 15 over 4. Now simplify a little bit. Lateral log of 1 is 0. 1 to negative 15 over 4 is 1. Then we get the result here. This is the value of this integral. Example 2. Find the land area and the area of the region bounded by this function and the x-axis on this interval. In this diagram, I have plotted the region, the shaded region. Now, this example has 2 questions. Question 1, find the land area of the shaded region. Second question, find the area of the shaded region. Land area is total area above x-axis minus total area below x-axis. Area, second question, area here means the total area. It is total area above x-axis plus total area below x-axis. Now, let me answer the first question first. Find the land area. To find the land area, we just need to take integral on the function. Yeah, we just need to compute this integral. By formula, to compute this integral, we need to find antiderivative for 6 times cosine. One antiderivative is 6 times sine. So by formula, this integral is antiderivative, plug in pi, upper limit, plug in lower limit in x. So the value of this integral is 6. That is total area above x-axis minus total area below x-axis is 6. Now, second question, find area of this shaded region. Area now means total area. To compute total area, we need to compute integral on absolute value of the function. Yeah, we need to compute this integral. Absolute value on 6 times cosine. This is total area. Because the function now has absolute value, to compute this integral, we need to remove absolute value. Otherwise, we cannot compute integral. Okay, now to remove the absolute value, let me split this integral. Integral is area. This integral is from negative pi over 2 to pi. Let me split this integral into a sum of 2 integrals. The first integral is negative pi over 2 to pi over 2. Yeah. The second integral is pi over 2 to pi. Yeah. Okay, now for these 2 integrals, I can remove absolute value. The first integral, x is between negative pi over 2 and pi over 2. X between negative pi over 2 and pi over 2. On this interval, the function is positive. So absolute value of a positive function is the function itself. Absolute value has no effect, has no effect on positive function. So I can directly remove absolute value. Okay. Now, second integral, x is between pi over 2 and pi. When x between pi over 2 and pi, the function is negative. Take absolute value. Now, when we remove absolute value on a negative function, don't forget, add a minus sign in the function. The minus a negative function is positive. So when we remove absolute value on a negative function, add a minus sign to keep the function positive. Okay. Okay. Now, now these 2 integrals, they have no absolute value, so I can compute their values. First, 6, negative 6, they are constants. I can move them outside the integrals. So move them outside the integrals. Now, to find this integral antiderivative of cosine, it is sine. So this integral by formula is this number. And again, the second integral is this number. This number. Now, plug in upper limit pi over 2 in x, plug in negative pi over 2, the lower limit in x, then we get this equation. Plug in pi in x, plug in pi over 2 in x. Yeah. Then make a difference. Okay. By calculator, sine of pi over 2 is 1. Sine of negative pi over 2 is negative 1. Sine of pi, 0. Sine of pi over 2, 1. Then we get the number is 18. So this integral, the value is 18. That is, the total area of the shaded region is 18. Yeah, it's 18. Example number 3. In this example, we cannot use fundamental theorem of calculus. To use fundamental theorem of calculus, the function should be continuous. But in this example, the function not continuous. Okay, now example 3. What is wrong with the following calculation? Okay, calculate this integral. Here, let me plot the graph of the function in this diagram. Okay, yeah, the red curve is the graph of the function, At 0, when x is 0, function has no value. At 0, the function approaches positive infinity. This integral is the area of the shaded region. Yeah, the area of the shaded region. This integral is area of the shaded region above x-axis minus area of the shaded region below x-axis. This region has no part below x-axis, so a below is 0. So this integral is equal to only a above. A above, area is a positive number. Area cannot be negative. So this integral, geometrically, graphically, we can see that this integral is a positive number. But let me try to use fundamental theorem to compute this integral. See what will happen. 1 over x squared antiderivative is this guy. Okay, now let me simplify this guy a little bit. It is a negative 1 over x. Okay, so plug in upper limit 3 in x, plug in lower negative 1 in x, the lower limit, okay, then make a difference. So this symbol means this number. This number is negative 4 over 3. So fundamental theorem says that this integral is a negative number. Then what is wrong? Okay, we get a different result. Geometrically, we can see that this integral is positive. But fundamental theorem says that this integral is negative. The problem is this function is not continuous over this interval, not continuous. Yeah, we cannot draw the graph of the function, okay, without removing our pen from the paper, not continuous at the point 0. So fundamental theorem cannot be applied to this, to compute this integral. Fundamental theorem, the condition to use fundamental theorem is the function should be continuous. Otherwise, don't use fundamental theorem. Then fundamental theorem doesn't hold for a function that is not continuous. Example number 5. Evaluate this integral where the function is a piecewise defined function. The graph of this function is here. From negative 2 to 0, the graph is this horizontal line. From 0 to 2, the graph is this parabola. Function f is not continuous at the point 0. At the point 0, the graph has a jump. Because the function is not continuous from negative 2 to 2, we cannot directly apply fundamental theorem to compute this integral from negative 2 to 2. The condition to use fundamental theorem is the function should be continuous. In order to use fundamental theorem to compute this integral, we need to split this integral into a sum of smaller integrals. Okay, here I split this integral from negative 2 to 2 into an integral from negative 2 to 0. Negative 2 to 0, the function is continuous. Plus the integral from 0 to 2. From 0 to 2, the function is continuous. So we can apply fundamental theorem to compute these two integrals. This integral x is between negative 2 and 0. When x between negative 2 and 0, the function is 2. So f is 2. This integral is this integral. When x is between 0 and 2, the function is 4 minus x squared. So this integral is this integral. The second integral is an integral of a difference. So by subtraction by difference rule, I can write this integral into a difference of two integrals. Okay, now apply fundamental theorem to compute each of these three integrals. First integral, antiderivative for 2 is 2x. Antiderivative for 4 is 4x. X squared antiderivative is x to the third over 3. By fundamental theorem, by formula, this integral is this number, and this is this number, and this is this number. Now, plug in 0, plug in 2 in x, and plug in 0 in x, then 0 minus plug in 2 in x minus negative 2. Plug in 0 in x, 0, plug in negative 2 in x minus negative 2. And similarly, plug in 0 in x minus plug in negative 2 in x. Calculator, then we get 28 over 3. So the area of this region is 28 over 3. Example 6. If f is the function whose graph is shown in the following figure number 1. Figure number 1 is here. This curve is the graph of the function f. Now, suppose a of x is this integral. The integral from 0 to x on the function f. This is the net area of the region between 0 and x and between the graph of f and the t axis. X is a variable. Now, two questions. Question A. Find the values of the function a when x is 0, 1, 2, 3, 4, and 5, respectively. B. Question B. Based on question A, sketch a rough graph of the function a. Okay, now let me answer question A. To find a of 0, plug in 0 in the x here. Then a of 0 is this integral. This integral is the net area of the region between 0 and 0. The region between 0 and 0 is a 9. A 9 has low area, so this integral, the value is 0. Now, a of 1. Plug in 1 in x, then a of 1 is this integral. This is the net area of the region between 0 and 1. The region between 0 and 1 is this triangle. This triangle completely nice above the t axis. So the net area of this triangle is the area of the triangle. This triangle, the base is 1. The height is 2. So area is 1/2 times base times height is 1. So therefore, this integral is 1. Now, a of 2, plug in 2 in x, then A of 2 is this integral. It is the net area between 0 and 2. Between 0 and 2. I want to use what I got here. Integral from 0 to 1 is 1. I want to use this information. So I split this integral 0 to 2 into the integral 0 to 1 plus 1 to 2. 0 to 1 is 1, so 1. Now what I need is to compute this integral 1 to 2. 1 to 2 is the net area of the region between 1 and 2. The region between 1 and 2 is this rectangle. Again, this rectangle lies above the t-axis, so the net area of this region is the area of the rectangle. The base is 1. The height of the rectangle is 2, so area is 2. So the answer to A of 2 is, this is a 1. This is 2, so the answer is 3. Now, A of 3. Plug in the number 3 in X, then A of 3 is this integral. I split this integral into the integral from 0 to 2 plus 2 to 3. 0 to 2, I got it. It is number 3. Now, let me compare 2 to 3. 2 to 3 is the net area of the region between 2 and 3. It is this region. This region, the boundary here is a curve. In this example, we are not given the formula for the function f. So I cannot use fundamental theorem to compute the integral between 2 and 3 on this function. So what I need is to guess. So what I can do is to guess the area of this region. I cannot exactly find the value of the area of this region. How to guess the area of this region? I use a triangle. Use this triangle. This triangle, the base is 1. The height is 2. So this triangle, the area is 1/2 times base times height, exactly 1. This region, graphically, I can see that this region is slightly larger than the triangle. So I guess on its area is, say, 1.3, right? The triangle, the area is 1. The region slightly larger than the triangle. So I guess the area of the region is 1.3. So, okay. Now, this integral is 1.3. And this integral is 3. So their sum is 4.3. So the value of A of 3 roughly is 4.3. Now, A of 4. Plug in 4 in X, then A of 4 is this integral. Write this integral as integral 0 to 3 plus integral 3 to 4. Integral 0 to 3, this integral is 4.3. Now, let me compute integral 3 to 4. Here, integral 3 to 4. Integral is net area, so this integral is equal to area above the t axis minus area below the t axis. Now go to the diagram. Integral 3 to 4 is the net area of the region between 3 and 4. The region between 3 and 4 is this region. This region is now this time completely lies below the t-axis. So this region, the area above the t-axis is 0. Yeah, this is 0. A above is 0, so 0. Now let me guess. A below, the area below, okay? The area below t-axis is the area of this region. Again, I use a triangle, this triangle to guess on the area of this region. This triangle, the area is 1. And the region slightly larger than the triangle. So I guess the area of the region is 1.3. So yeah, here, area below is 1.3. So 0 minus 1.3, negative 1.3. This integral is negative 1.3. So here, this integral is negative 1.3. And this is 4.3. So 4.3 plus negative 1.3 is 3. So the value of A of 4 is 3. Finally, A of 5. Plug in the number 5 in X. Then A of 5 is this integral. Split this integral into integral 0 to 4 plus integral 4 to 5. 0 to 4 is number 3. So 3. Now guess the integral 4 to 5. 4 to 5 is the net area of the region between 4 and 5. The region between 4 and 5 is this region. The net area of this region is area above. It is 0 minus area below. Area below is the area of this region. Again, I use a triangle, this triangle to guess the area of this region. So my guess is again 1.3. Therefore, this integral net area is negative 1.3. So a sum, this sum is 1.7. So the value of this is 1.7. This is the answer to question A. Now, question B. Based on A, sketch a rough graph of the function A. In part A, I got A of 0 is 0. That means that the graph of A passes through the origin. Yeah, this point is on the graph of the function A. A of 1 is 1, so this point is on the graph of the function A. A of 2 is 3, so this point is on the graph. And similarly, A of 3 is 4.3. Now, this point is on the graph. And A of 4 is 3, so this point on the graph. A of 5 is 1.7. Yeah, this point is on the graph. Now, I plot the data points that I obtained from part A. Then use a curve to connect the data points. This curve roughly is the graph of the function A. From this plot, I can see that function A reaches its maximum when x is 3. Beyond the point 3, the curve is decreasing. the value of the function is decreasing beyond the point 3. It is because a of x is an integral. Integral is the area a above minus a below. When x is larger than 3, say x is here, for example, suppose that x is here, then the integral is the net area between 0 and x. Net area of the region between 0 and x. When x is larger than 3, area below is non-zero. Actually, when x, if you move x in this direction, in the positive direction, then area below actually is increasing. Area below is increasing, right? The total area below T axis is larger and larger as the point x is moving in the positive direction. So that area a above is a constant when x is greater than 3. Minus a below is increasing. So the value of this integral is a above minus a below. A below is increasing. So the value of this integral is decreasing. So as x is moving in the positive direction, the graph of a is decreasing.